Okay, so today we're going to start on arithmetic and branching, some of the statements in our language. We just finished up functions, the calling convention that we have in System 5 for x86-64, how we handle freezing the state, local variables, restoring the state of functions after a function call. And yeah, so we're going to actually do the body of functions now. We're going to do the statements in simple IR. And today we're going to start with arithmetic. But before I get in, questions on anything with functions? Questions on the programming assignment? Yeah. It's what? Printout state? A lot of what? Mm-hmm. I'm sorry, say again?
A lot of like the instructions for cogen, right? For like a column, we have to, like emit. Do you print?
Yeah, you just print it out. This is the compiler term for print it out. Now, in a real compiler, you wouldn't necessarily just print the standard out. You may have a data structure that records the output language. But yeah, remember, the compiler is really just reading in a text file that's source code in some language and printing out a text file that's source code in a different language. So the simplest way to do this is literally just print out the text. So yeah, that's what emit means. Other questions on project? So this is due next week. I think that's Monday, right? So CoGen 1 is due Monday. It's probably one of the harder ones. Pointers is hard to understand, but the coding is simple. This is probably I would say the hardest or the most extensive part of the compiler project. Arithmetic and branching should hopefully be a little more straightforward. Any other questions on the coding project? And remember, of course, you can always resubmit or submit after the deadline, up until the final project deadline. Yeah. No, let us know on EdStem. You can send a private message, ask for a regrade, but yeah, we don't do it automatically. It's please request it. Okay, hopefully functions is somewhat clear. I know there's a lot of sort of technical details because of the calling convention, but that's actually how the system tools work on Unix-like systems with Intel 64-bit. This Intel 64-bit architecture, or I should say the AMD 64-bit architecture. All right, let's go over the homework. So for the homework, I repeated some of the questions from the first class because I actually didn't get to all of them in the first class. So I'll go over them really quickly. So in the x86-64 System 5 ABI, which is the calling convention we're using for our compiler, how are parameters passed? In a function call, how do parameters get passed? Any takers? Second. Yeah.
The first six are like RDI, and if there's specific names, I can't remember.
Yeah.
I remember the first six get passed in, and the rest of them get passed in differently.
Yeah, that's right. So the first six are passed in via registers. Yeah. So there's six just conventionally defined registers that you store or move your values into for the first six parameters, and then for the rest of them, you push them on the stack. So yeah, that's exactly right. The 32-bit ABI, System 5, it's all stack pass parameters. So it's a little easier to implement for us, the compiler writers. But so for efficiency's sake, I guess, because registers are faster to store to, the x86-64 version of this ABI uses the first six for registers. And this is just a convention. There's nothing intrinsic about the AMD 64 architecture that is these registers are for parameters. It's just a convention. Okay, so I asked again where for the stack frame, whether it's the calling function or the called function, the caller or the callee, who sets up this part of the stack frame? For stack parameters, is that the caller or the callee that sets the stack parameters? The caller, yeah, the caller. So when there's a function call, if you just think about in C, when you call a function, so you call function f, you pass parameters, it's the calling function that evaluates the values of those parameters. So it has those in its function local state. or has access to it from its local state. And so it sets the parameters, pushes those parameters onto the stack before it actually executes the assembly call instruction. Okay, return address. Who sets the return address? This is the callee. Oh, sorry, the caller. Yeah, the caller. The return address, the caller. So again, when the calling function is issuing the call, the next instruction, the return address, is just the next instruction after the call instruction. So the caller sets the return address. What about local variables for a function? Is it the caller or the callee that allocates space for these in the stack? The callee allocates space for it. And what about the old base pointer? So first of all, what is the old base pointer? What is the base pointer? Yeah. Yeah, it keeps track of the base of the stack frame. Keeps track of the stack frame. Gives you access to the local variables. And so for the old base pointer, who adds that to the stack? Is it the caller or the callee? And so the caller is the old base pointer. So I'm talking about the caller's base pointer. Issues the executes the call instruction, goes to the callee. So that previous base pointer, the caller's base pointer, who stores that on the stack? Caller or callee? Callee, right. It's part of the prologue of every function call. And so what can be kind of confusing about when you're writing the compiler for this is that the caller and the callee are both functions. They both have their own prologue and their own epilogue. And you just have to track in your mind when you're writing out a function. At the beginning of every function call, or beginning of every function definition, you put the prologue. The prologue pushes RBP, pushes the base pointer. That's the previous setting of the base pointer before that function gets called. So the old base pointer is saved by the callee. Questions on this homework? Yeah.
Like, when we're using the example with the main function calling the function out, it registers the old base pointer first, and then it goes to the callee.
Yeah. Wait, say again?
So whenever you did the example you took the last class, you showed the main function calling function. And I might be calling this a lot 100%.
You mean in the stack frame?
Yeah, exactly, yeah. So the main initializes the old base pointer first for F, and F changes it, correct?
Actually, not quite. So main has its own old base pointer, but that's the base pointer of whoever called main. So this part here, this is after function F is starting to execute. So after main executes the call instruction, the stack looks like this, or actually looks like this. Well, before we do the call instruction.
After main, right? It goes below main in the stack, and then it starts doing the calls for F. But well, in this case, it's main's above F. So once
main
calls F, it goes below F.
Yeah, so once the call happens, the return address gets pushed by the call instruction, and then we're here. And once and then we branch to F, and when F starts executing, the first thing it does in the prologue is to push the old base pointer. So this base pointer here is a pointer to main stack frame, if that makes sense.
Yeah, thank you.
Sure, yeah. So this is what makes this kind of tricky to wrap your mind around, in the actual technical steps of the assembly file. But conceptually, what's going on here is each function call has its own stack frame, and part of that stack frame has the return address for the caller function and also the stack frame for the caller function. And these two are what is going to allow us to restore the state of the calling function, of the caller function. So this is how we get back to the function that called us. But that information is stored in the callees in F's stack frame because F needs to have access to it. So when F is done, it needs to be able to know where in the stack to find that information to be able to restore the state of main. Okay, other questions on functions? Questions on the project, CodeGen 1? Yeah. Yeah, well, so there will be parameters. But because the base pointer points here, base pointer always points to the old base pointer, you can always get to the base pointer as just offset 0. The old base pointer in this calling convention is always at the address pointed by RBP. So we point at a fixed position in the stack frame, And then if you go +1, you get the return address, and then plus whatever, you get the stack allocated parameters. If you go minus something, you get the local state. So the stack frame, by convention, is always the pointer to the stack frame is always kind of in the middle of the stack, a spindle of the stack frame where the old base pointer is. And incidentally, this actually makes basically a linked list of stack frames. So if you follow you follow the old base pointer links, and you have like 10 function calls, you'll have a linked list of stack frames, basically. If that makes sense. I didn't show more than 2, but yeah.
So like whatever our first function is, that base pointer that gets initialized first is basically getting linked to every base pointer that's getting put in those other functions. Columns.
Yes, but backwards.
Okay.
So it's the pointer goes from the new to the old. So it's what you said, but reverse. So you have your most recent function. You follow its old base pointer, it goes to its caller. You follow that base pointer, it goes to its caller. Follow that base, it goes to its caller, and so on until you get to the first function call. And so this is if you've ever seen like a stack trace. Who's heard of a stack trace? So in debugging, a stack trace tells you which functions have been called to get to where you are in the program. This is how you can find the stack trace, or one way. You can find the information from the function. So if you have extra debugging information in here, then you just follow these base pointer links to find the entire sequence of calls that led to where you are in the program. You can call this the call trace, or the call stack trace rather. So this is the call stack. Stack trace is where you print out the information from the call stack. All right, good questions. Other questions on function calls? Yeah.
I don't know if we've mentioned this already, but I understand you have more arguments than 6, then they just get put on the stack and be a string, and you just go -8 plus whatever you need to stick the memory above it. But how
Yeah.
does the current stack frame know how many parameters were pushed?
Oh, that's a good question. So the question was, okay, yes, we have parameters pushed onto the stack, but how does the current function f know how many parameters there are? So let's take C, for instance. If we define a function f, how does the compiler know how many parameters f takes?
Based on whatever's in parentheses.
Yeah, it's in the definition, right? So the compiler writer requires the developer to tell it how many parameters there are. So when you see a function definition like so you have function definition, like let's say we take the max function. This is why we have function declarations. The function declaration lists how many parameters there are and also their types, which tells us how much space we need for each of those parameters. And because we're generating the assembly version of this function when we process this definition, we as the compiler writer in the parse tree have a list of all the parameters. And so whenever we generate code that deals with parameters, we as the compiler writer, within the compiler, we have a list of all of these parameters in our parse tree. Yeah, so yeah, exactly. So by the time the code is being run, the compiler has already generated the right code to be able to access the parameters. If that sort of makes sense.
So basically from any frame of reference in any stack frame, the processor knows that function has this many parameters, basically, because it's already been.
Well, it's not so much, so there's nothing in the architecture that enforces this. It's that when we generate the code, we will only generate code. So it's like, let's say we access D. D is the 7th parameter here. We as the compiler writers know that at runtime, because we emit the assembly code ourselves, we know that this value will be here on the stack. We know that it will be on a specific part of the stack. So we generate code that will access RBP with that offset from RBP. So there's nothing actually at runtime that provides these guarantees. It's because when we generate the assembly code from the compiler, we know this information. We use that to ensure the guarantees. That makes sense. So this is like kind of the key part of compilation, like compile time versus runtime. You don't actually need any runtime, like you don't even need runtime functions. The architecture doesn't need to support actual functions. We can emulate it with the compiler by mapping it to what assembly supports, but by maintaining these conventions at runtime, maintaining the stack frame conventions at runtime. So this stack frame, there's nothing in the architecture that enforces that you use the stack frame correctly. It's you as the developer that would have to do that. And we as the compiler writer just can generate code that will ensure that those conventions are met. So this is kind of the mind-warping part about compilers, is that we're targeting a language that doesn't support any of these features. It doesn't support fixed numbers of parameters or even really different data types very much. It doesn't have like structs or anything. We're simulating those by generating code that will behave as if we had structs and function calls. So it's a little hard to explain. It gets a little philosophical, I guess. But yeah, that's what we as the compiler writers are doing. We're kind of emulating this input language on with another language that doesn't have support for those features. And we do it using the same tricks that I showed you in class. Like we maintain a symbol table at runtime that keeps track of all the local variables and what offsets we're going to allocate them at runtime, so that when we generate code that will be guaranteed to follow those conventions at runtime. That's really the tricky part. The compiler's not trying to compute the result. It's trying to rewrite the program in a different language so that it will have the same result. So it's kind of tricky to wrap your head around. And I think so that's why I kind of did the back end in this part, because it shows you kind of the first, lowest layer of this kind of compilation and this kind of simulation of languages. But if you're interested, take programming languages, take compiler construction. We'll see other techniques. So for instance, one technique that you see in your compiler is type errors, type checker errors. So if you've ever, for instance, somebody could call max with only 2 parameters, or say they call max with 10 parameters, well, that's going to cause a problem at runtime because, or let's say they only call it with 6. Let's say 1, 2, 3, 4, 5, 6. So if we try to access parameter D here, if our caller never actually pushed parameter 7, and the callee is trying to access parameter 7, well, it's going to access some state inside of the caller. It's not going to actually access parameter 7 because the caller didn't follow the function protocol properly. It didn't use the right number of parameters. So what the type checker does, one of the things it does, is it makes sure that anyone calling max will use the parameters correctly. We'll have the right data width, we'll have the right number of parameters. Because otherwise, if you didn't have that, then at runtime, it wouldn't follow the convention, right? So I only pass 6 parameters, I expect 7. When I go to access the 7th parameter, I'm not really accessing the parameter. So in order for this kind of simulation, this illusion to work, the callers also have to follow along and also have to follow the convention correctly and do the right thing. So one thing the type checker does is checks the program to make sure the compiler will be able to correctly generate code that actually matches the input language. So type checking is a huge area in computer science. We go into it a little bit in compiler construction, a little outside the scope in this class, but as soon as you start having a symbol table, you're recording information about the input language, you can start automatically checking. So for instance, if we had a symbol table that recorded max and said, all right, max has 7 parameters, then whenever we see a call to max, we just check our table and say, oh, is it called with 6 parameters or 7 parameters? How many parameters is it being called with? And if it's not right, then we as the compiler writer can just fail. Just say, developer, you messed up. Go do it again. Go satisfy these requirements. And that's where your compiler errors come from, or at least part of them. So that's where when you get type errors, that's where they come from. Other things that the compiler can check are uninitialized variables. So if you declare a variable and then don't set it before you print it, we can also use the symbol table to check that as well. So we can check, okay, at this point here, has CC been defined? Has it been assigned to anything? No. Then we as the compiler writer can check that. And even before the developer gets to running a program that may have some wrong behavior, we can warn them ahead of time and prevent them from generating bad code. And you can even use these type checker techniques for bug finding. So there are techniques that will check for null pointers or array out of bounds. And so you can extend this concept of checking the behavior of a program at compile time to the problem of bug finding and even security auditing. You can automatically check the security of the program. There are bounds to this. So there's a famous result by Turing called the halting problem, where he demonstrated that in general, there are certain questions that you can't answer about a program. So the halting problem was, can you write a program? So for instance, take a compiler. Can you input a program and tell whether that program ever terminates or whether it loops forever? So that kind of simple, it's kind of a simpler compiler question, right? So let's say we want to have a compiler that doesn't translate programs that run infinitely. We don't want infinite programs. So can you write a compiler checking phase that will tell you whether a program ever runs forever or terminates? And he showed, at least in his model of computation, that that's logically impossible in general. So you can do it for some programs. For instance, if I have a program like this, well, I can just do a string match to C. I can just match this string and say, oh, if the program says, well, actually in C it would be while 1. So I could just write a parser or write a regular expression that checks, is this in my program? If it is, then it runs forever. The problem is I could have also said something like while 2 minus 1, or while 2 times 3 plus x minus 4. And you can get an arbitrarily complicated program, and it's actually logically impossible to prove whether this program will always terminate or always run forever. So take a theory of computation class to go in more into that. Probably it might be a graduate level one to get into Turing completeness, but it's a pretty kind of clever result. Discrete 2. Discrete 2 does it? Okay, discrete 2. So you'll learn about the halting problem. And there are ways around this. There are ways to kind of do approximation that will still allow us to give us answers within some, while still accepting some false positive answers. But anyway, take compilers, take program analysis or discrete 2. You'll learn more about this. But yeah, it's an area that I work on a lot. I think this is a cool area. You can take this compiler technology and use it to actually answer more sophisticated things about the program. You can tell whether programs are correct or wrong or insecure within some pretty interesting limits. Getting around those limits is the kind of intellectually interesting part of that problem. Okay, so anyway, that was a big digression on type checking. But yeah, so that's at its core, this is what a type checker does. Simplest, it just makes sure that you're using functions correctly, using variables correctly, so that when the compiler goes to generating at runtime, you got to have expected behavior. All right, other questions on functions, the coding problem, homework? So I've put the Cogeneration 2 project up. Most of the information you need is already in the Cogeneration manual, but this gives you the instructions for setting up your repo and getting the code template again. And so this will be a separate project. So Cogen 1 will be its own compiler. You'll create a new repo, a new directory, download the template again, and kind of start fresh with a fresh compiler, but you'll only implement the functions, the listeners for the arithmetic and branching.
So we're going to get basically new given ones for all of that we just did.
Yes, you'll be given new given ones. So you could in principle use Cogen 1 as your starting point. The problem is Cogen 1 is necessary to even run branching and arithmetic because we need the right calling convention to have main and have it run. So feel free to use Cogen 1 if you like. It's a little bit of a risk because if that's broken, then all your tests will fail. But I've given you an alternative. So I've given you kind of specially hard-coded. So the problem is, if I just gave you the answers, well, that would be just Cogen 1's answers. So what I did was I've given you implementations of the function listeners that hard code the assembly for this simple IR program. So just to provide you some context for what this means. Remember that this is what our compiler does. We have this program written in C++. It takes simple IR text files and prints out assembly text files. And these programs should be equivalent. All the inputs given to the simple IR should give the same output as those inputs given to the assembly. So what I've given you is I've given you. So what I'm going to do is I'm only going to test you using this simple IR template. So it'll always have these exact variables, and it'll always call this print function, and it'll always return 0. And then inside the body of it, that's where you add your code to test. That's where I'll put different code to test, arithmetic and branching code. So if we generate this simple IR, if we generate assembly for it correctly, this is what the assembly file, I didn't show you this assembly file, but this is what the assembly will look like, the assembly code will look like for this simple IR. So this is like the correct translation of this simple IR program. And then right here, oops. Right here is where the code for arithmetic and branching will be generated. It'll start being generated here. So if you were to implement only the arithmetic and branching code, all of this will be empty. You just have like the middle of an assembly file. So what I've given you is implementations of these functions, these 5 functions that hard code the output for this simple IR program. Does that kind of make sense? Sort of? So it has hard-coded assembly code that will only work for like one simple IR function, if that makes sense. So if you just use these implementations of the function five functions and only use this as a template for your simple IR, then your program will be correct, will correctly implement functions. Does that sort of make sense? So the way you use this is you take this template, copy it. Don't just save lots of test cases. Don't just have one test case and change inside, because then you lose the ability to do regression testing. But copy it, then compile it with your CodeGen to assembly, and assemble and link it with GCC as usual and run it. So you just copy this template, make a new copy of this template, add the code you want to test here, because you only need to test arithmetic and branching. Make sure you only use these variables if you're going to use for testing. And then it should work as normal. The function stuff should work as normal. Does that sort of make sense? Let me know on EdStem if you need like more specific directions on this. I sort of gave you an overview of how this works. But as long as you just copy these functions, these hard-coded assembly functions, and only use these variables in your tests, then it should just work correctly. I did this last semester as well. I kind of simplified it here, how you use it. So it should just work. Let me know on EdStem if you have any issues or any more questions about it. So one other wrinkle here is that for testing purposes, I have this call a function that will print the result variable. So always put your result in the result variable and it'll be printed out. PrintInt is just a C function. So you can just use this C function here. And because we've implemented function calls using the System 5 ABI for x86-64, we can actually call C functions from simple IR. So this is calling a C function passing result as the parameter, and this is the C implementation of that. And because we're following this calling convention, we can just pass that C program to GCC, and it'll compile and link it with our program correctly and give us an executable. Pretty cool, right? Because we're following the convention, we can actually use the rest of the system tools to call and actually be called from C programs. You could actually write simple IR functions that get called from C, and you can interoperate between the two languages. So that's kind of technical details behind it. But at the main point I want to get across is that if you use these hard-coded listeners for the CodeGen 1 functions in your CodeGen 2 project, and you stick to using this template, which means you only use these variables and put your result in the result variable, then you'll be able to test arithmetic and branching without having to implement CodeGen 1 first. So just try it out and follow these directions. Take this io-lib.c and use it. Compile and link your output of your compiler with it, and you'll have, it'll work. The simple IR function stuff will work. Questions on that? So that's really the main thing I want to just get across here. So I've given you a table of what to implement. So use these functions again. They're already given to you in the handbook. So remember, this is a new compiler, new project. Start from the template fresh and re-implement these functions that I've given to you already. Use the hard-coded versions with that IR template, with that simple IR template. And then then you only have to implement 4 listeners on your own for arithmetic operations and branching. Otherwise, everything's the same. So I haven't put the tests up yet. I'll put the tests up soon. But yeah, this is all you need to actually implement on your own are these 4. With just a little setup, set up the rest of the functions. All right, questions? Questions on this? Okay, so let's see how we actually do arithmetic. So we'll learn first about how arithmetic works in x86-64, and then we'll see translation strategies, how we actually can take simple IR's arithmetic and translate it to x86-64 assembly. Okay, so what we'd like to ultimately do is take simple IR arithmetic. So remember the semantics of this, remember the behavior of this. This is taking whatever the value of A is at this point in the program, whatever the value of B is, performing integer arithmetic, and then assigning the result to X, the X variable. Questions on that? Pretty straightforward, right? Just like in C. And so this is what the Intel x86-64 assembly looks like. We have an add mnemonic and 2 operands. So we've got 3 variables here and 2 operands here. What's the difference in the semantics here? Is MIPS use 3 operands or 2 for add? Does it have a destination or does it overwrite? It has 3. So the Intel world, we have 2. So what happens? The destination operand is both the left operand and also the assignment. So this is, I think I show it here. Well, let me get there. But so in the Intel world, add RBX RAX is equivalent to RAX equals RAX plus RBX. So this is AT&T syntax, so notice that the operands are the reverse of what you'd expect for addition. That doesn't matter for addition. But this right operand, this is the left operand of the addition and also the destination, the value that gets stored in. So you can kind of see already that even though both languages have an addition, their semantics are really quite different. And so this is what the compiler is doing. It's translating between the meaning of simple IR addition, which has different behavior, and trying to translate it to whatever Intel gives you in that language. Yeah?
Is there a comma between?
Yes, there should be a comma here. Good catch. Yeah, there should be a comma there. I'll fix it for the notes online. Okay, so as you can imagine, there's a bunch of challenges here. So first of all, we don't have variables here. We have registers or memory locations. How do we deal with integer constants? We saw that already. So if we have integer constants, that's represented differently in assembly. And assignment itself. So how do we convert something that has 3 variables to something whose semantics has 2? So these will be our challenges to translating arithmetic operations. Okay, so let's recall the simple IR grammar. So this construct is called an operation. So this here, the ANTLER parser will recognize this entire statement as an operation statement. And its syntax is some name followed by this colon equals punctuation symbol. And then the operand is either a name token or a num token. So num represents constants. That's followed by one of these 5 operators. So these are the tokens for operators, plus, minus, star, slash, and percent sign. Because remember, they don't have their meaning until the compiler actually translates them into something that gives a meaning. These are just ASCII symbols for percent. And then that's followed by the right operand, which can either be a name or a number. Questions on the grammar of this? So it's just variable name equals variable or number, operator, variable or number. That's the syntax of an operation in simple IR. Questions on that? So going back to the compiler basics, it's the parser that figures all of this pattern out for you and gives you a parse tree that allows you to access each part of this statement. That allows us to access the destination variable, the operands, and the operator. Okay. So just getting back to our example here, the name for our operation, that first name is X, the operands are A and B, the symbol's A and B, and the operator is the plus symbol. And just as a reminder, that name or num, that name slash num, in simple IR assignments, you can also give constants instead of variables. And yeah, these are our 5 operators available. Okay, so let's look at how first we can access the operands. So how do we translate an access of the variable A, for instance, into an assembly operand? How do we translate that? Or how do we represent that in assembly? How do we represent variables in assembly? Okay, you could use registers. In our compiler for Code Gen 1, when we, how did we allocate space for variables? The stack, right? So we use this convention where we allocate space on the stack for every variable. And when we wanted to do an assignment to that variable, we translated the assignment to a store or a load. And that store or load was to the stack frame. Now, in real-world compilers, yeah, you can also represent variables with registers. And if your compiler is really clever, you can figure out that you actually never need memory locations for your variables and only use registers. But that's much harder. And we have a finite number of variables and a potentially unbounded number or finite number of registers and unbounded number of variables. So for our compiler, we're always going to use the memory location to represent our variable. Okay, so they're in memory in the stack frame. How did we access a given variable on the stack frame? So we don't know its address at runtime, or at compile time, right? Because there may be several calls being made. Yeah, how did we access it? Yeah. Yeah, we use an offset from the base pointer. So we use this assembly operand syntax to say, whatever the current base pointer is, subtract 16 bytes and access that memory location. So this, if A is at -16, offset -16, then this is how we can access or load that memory into a register. Questions on that? So this is what the calling convention and the function local state, all that work we did to simulate function local state, this gives us a scheme for translating variable accesses into assembly operands. Questions on that? So that's what we did like the past week and a half, was how we can set up the assembly code so that our variables can be accessed just by offsets from RBP. And all that, saving the old base pointer and restoring it, making sure the base pointer always pointed at the stack frame, enabled us to be able to translate variable accesses into these operands, these Intel assembly operands. Okay, so this is how we can access a variable. Now, what about integer constants? I think we saw this already. Those are simple to translate in AT&T syntax. We just take whatever the ASCII number was in the simple IR and generate the same ASCII codes, but with a money sign before it, $sign. So this is the syntax in assembly for representing constant integers. Okay, what about saving the result? So how do we store to variables? Well, it's the same idea. We just use whatever the variable name is, translate it into this operand that represents an offset from the base pointer, and use it as the destination. So the right operand is the destination of the move, the left operand is the source. So if we want to assign a variable, we just take whatever value we're trying to assign and store it to that location. Questions on that? So kind of a little review of function local state. Okay, so let's see how arithmetic works in the Intel world. So as I alluded to before, the meaning of this add instruction, so this is saying add RBX, the B register, and RAX, this is equivalent in like C, a C-like language to this, where we take RAX as the left operand of the addition. It's the right operand of the assembly instruction, but it's the left operand of the addition. Do an integer addition to it, with that and BX, and then store the result in RAX. So this is overwriting the RAX register. So if you were sort of hoping to be able to map a variable to a register all the time, it's going to make things a little tricky, right? Because if we always wanted RAX to be a single variable and we had something like x equals a plus b, well, we're going to blow away RAX here. We're going to lose that value. So this is why in our compiler scheme, I recommend we always use memory to back the variable instead of trying to keep them in registers. So little different semantics to keep in mind, but this is both the left operand and the destination of the result of the addition. So a little different from MIPS, where you have to give three operand. We have to give all three of those as separate registers. So A is sometimes called the accumulator register. So historically, it was used as it was a special purpose register for doing like addition and increment. Questions on this? Questions on this semantic difference between simple IR or C and assembly? Okay, so this is subtraction. Subtraction, we just use the sub mnemonic. And same behavior applies. RAX is both the left operand of the subtraction and the destination. So let's see what happens if we mix up these operands. So remember, AT&T syntax, the destination is the second operand in assembly. So what's the results of these two additions here? So I move 9 into RAX, 5 into RBX, and I add RAX to RBX. What's the result of this? What's the final state of these registers? Maybe I should actually write this down. So let's take this first example here, and we have two registers, RAX, RBX. So the move instruction sets RAX to 9. The move 5 to RBX sets it to 5. What's the result? What's the resulting state of the machine after I run this add instruction? Yeah. Yes, RBX goes to 14, because remember, confusingly, in the AT&T syntax for Intel x86-64, the second operand is both the left operand of the addition or subtraction and also the destination. So this will add 5 and 9, getting 14, and store the result in the second operand, giving us RBX being changed. Questions on that? Does that make sense? And similarly, for the second example, what's the result? So I move 9 into RAX and move 5 into RBX. What's the resulting state of the machine after running this addition? RAX will be 14 because we've made RAX the destination operand by putting it as the second operand. All right, so let's see what happens if we repeat this, but for subtraction. So same numbers, so RAX and RBX. We have 9 and 5. what's the result of this subtraction operation?
-4.
Yeah, is that what you were going to say? -4. -4 where? RBX. So RBX will be -4. And what if we swap the operands? So again, we have 9 and 5 same operands. What's going to be the state of the machine after this subtraction? 4 in RAX. So RAX is the destination operand. So notice, addition is commutative. You can swap the operators. Subtraction is not. So getting this right, yeah, it's important. Not only is the destination operand right, but the order of operands will change your result. So just as a reminder of the semantic difference in this AT&T assembly syntax from simple IR and C. All right, questions about that? So this is just the design of the architecture and the design of the assembly language. So in all examples that I'm going to give you, I'm going to use RAX and RBX, and I'm going to make RAX both the left operand and the destination. You'll see it in the example code and the example I go in today, and I'll just remind you. So I thought it was clear to have A and B as the first and second operands all the time, but the downside is we have to save RBX. We have to push it onto the stack because it's call-e saved. Okay, let's look at multiplication. So multiplication has the same operation ordering, except we use the imul mnemonic. So imul is for integer multiplication. We're only doing integer arithmetic in this language. So yeah, that's multiplication. Works the same way. Multiplication is commutative, so you get the same result, but in a different register if you swap these operands. Okay, so let's see what it looks like to translate this program, to translate this operation here. So I'm going to give these offsets to these variables, so don't worry too much about what they exactly are. This is just skipping RBX, which got pushed. That was kind of what I sort of hinted at last time. So these are the offsets. Any questions about why these offsets or what the offsets mean? Simple table. So this is what we covered in functions, that this local variables, there should be local variables, gives us 3 variables. We allocate them in the stack in these descending offsets, -16, -24, -32. Yeah? -8 would be RBX, because I'm pushing RBX. I may change this for next semester because it's too confusing to have this call these save stuff. I really just wanted to be able to say AX and BX. The problem is if you blow away BX, the calling function may have expected you to save it. And so you'll end up breaking the convention. But I may just change this to a different register like R9 or something. I don't know. But yeah, that's why. So just kind of accept these are the offsets that are going to be in your compiler. Yeah.
It kind of does make sense though, because I think whenever I see it, I kind of think of binary and 8, you just repeatedly going back 8 in a way.
It is, but what he was asking is why doesn't it start at -8 instead of -16? But yeah, once you have the first offset of the variable, yeah, they're all going to be 8 away because in this language everything's a 64-bit integer. If you're in like a real compiler, like a C compiler, these may be different offsets because integers in a 64-bit system, C integers are 32 bits. They're only 4 bytes. So if X were 32 bytes, this offset would only be to -20. It would be 8 bytes less. But anyway, okay. So these are the offsets into the stack frame of these local variables for our program. And so to do the translation, there are 3 parts. At least in the compiler recommendation I'm giving to you, there are lots of different equivalent translations of the IR, but this is, I think, the simplest. So there's 3 steps. First, load the variables to registers. So in the Intel world, you can only do a single load or store per operation. So you wouldn't be able to say something like, add -8 RBP and -16 RBP. You're restricted to 1 load or store per operation. So this is not possible. And also, if you did this, you'd end up, even if it did work, you'd end up overwriting your variable here. So if we were trying to do, well, I probably shouldn't say 8. I should probably say, let's say it's 24 and 32. Or, so if I was trying to add A plus B, I'd end up overwriting A, which I don't want to do, right? So the first thing we do is we use, so basically in this compiler, we're going to use the registers as kind of scratch space and use the memory only when we already have the resulting value of our variables. So we're first going to load the variables from memory into registers. Then we're going to perform the addition operation. We're not going to perform it. We're going to generate code that will perform it. And then we're going to generate code that's going to do a store to update update that variable's value. Make sense? Questions on this? So we decompose this operation into 3 steps. Loads for the operands, the actual addition operation itself, and then a store for the resulting variable's value. All right, here's what that assembly code looks like. So here's our loads. We take A and B, and remember A had negative 24 offset, B had negative 32 offset. So we do 2 loads, one for each operand. And we could choose any registers to store it in, basically, except like RBP or RSP. We could choose any register we like. To make things simpler on myself and for you guys, I'm always going to use RAX as the first operand and RBX for the second operand. There's going to be one exception to this because of how the architecture supports division, but I'm going to strive to use RAX and RBX for the 2 operands, just to make things kind of consistent, a little simpler. So here's our load. We load these 2. We generate code that will load the variable values into registers. Questions on this? So remember, this is getting pointing into our stack frame and getting the values of memory in the stack frame. So there's our loads. Here's our addition operation, recalling that RAX is both the left operand and the destination. So we generate an addition operand that operates on the registers. And then once we're done, we use a store to store into the offset that X is in. So X is negative 16. So we store our result, which is in RAX, because that's the destination of add, into X. And that's it. That's all you have to do for add. Questions on this? So when you're going to generate your code, you can really hard code the vast majority of this. And what's the only thing that changes for different additions? Like let's say I had, instead of X equals A plus B, let's say I had A equals A plus A. What would change in this assembly code? What's the only thing that would change in this assembly code? The offsets. Yeah, exactly. The offsets are the only thing that change here. So for every addition operation, this template correctly translates simple IR's addition into assembly. So whenever you see an addition operation, you can always just spit out this code and just change the offsets to correspond to the variables. So that's why I implemented the compiler in this way, because it's very template driven. You have mostly hard-coded assembly, and then you just change out the offsets or change out small parts of it to correspond to the parse tree. Okay, any questions on this code? Other questions on this code? And so remember that your compiler will be printing out or emitting or printing out this assembly code. And your goal as the compiler register is to make sure that it corresponds to the input language's code. Okay, so let's see a variation of this where we have constants. So here's a different program where we've got b equals 5 and then x equals 7 plus b. So let's translate this operation here. So we're not translating this, we're translating this operation. So to translate this, so what are the 3 steps? What's the first thing we do when translating this arithmetic expression? Yeah. Yeah, we load the variables from memory and registers. We only have B, so we only have one variable to register, or one variable to load. So for the other one, we just do a move immediate. We do a move immediate. That should not be negative, but we do a move immediate into RAX. So that's how we set the register for the immediate. Now, okay, so then what's the next step? We actually do the addition. We emit the addition. So this is identical, right? This is identical to what we had before. We just add RAX and RBX. Now you might be wondering, could you just take this immediate value and put it here? Yeah, you could do that. But I don't want to do that because then my template is more complicated. By separating into these three steps, my addition won't be influenced by differences in the arguments. I can just always emit the same addition for any arguments. And similarly, the last step is also going to be identical. We just move RAX into whatever is stored. So if I were making complicated decisions about registers or trying to be clever about immediates versus variables, I may have very different code generated for different simple IR. By using this simple scheme here, my template is always going to be very, very similar. It's going to be basically the same template. I just plug in different values for offsets, different values for the operation. And that's basically it. Okay, questions on this example? Oh, sorry, this example. All right, so division is where things get a little complicated. Oh yeah, sorry, go ahead. Couldn't I switch these? So let's see what happened when we switch these. So if this was, what's the values here? 7 and 5. So if you switch them, the result is going to be 12 no matter what, right? What's going to happen though, what am I going to store into X if I do that? So our AX is going to be set to 7. So X is going to be set to 7, right? Because our BX, if we swap these, our BX is going to get the value 12. And our AX is going to stay 7. And then X is going to have the value 7, right? Because we want the X to have the value 12, but because here we moved RAX into X. Now we could, swap them and then also use RBX here. But I want to reduce this complexity, so I want this template to be basically the same for all arithmetic operations. Now, feel free to experiment with other ways to generate code. This is the way I did it to make it simpler on myself. And so remember, you can always, what real compilers do is they do these very simple kind of template-driven translations, and then there are later phases that will automatically optimize, improve the code. All right, other questions on this example? Yeah. This is going to be the subject of compiler construction, but effectively you'll write something. You're in the compiler in the same way that we were able to record a symbol table keeping track of offsets for variables. We can record in a symbol table their constant settings, and then use that information. Like let's say here we keep track of the fact that RAX is always 7, then when we're here, we can observe the fact that RAX is always 7 and use that to rewrite this code in an improved way. So let's take compiler construction if you're really interested. I think it should be offered in the fall. But yeah, it's a little more complicated in this class, a little outside the scope of this class, but it builds on these compiler techniques to record information about the program that will be true at runtime and exploit that to be able to rewrite the program in ways that have fewer instructions or fewer memory loads and stores. But that's a semester-long tangent to go on. But the techniques are very cool, I think. They're closely related to that theory of computation and that work with Turing, trying to have a program that figures out what another program is doing. It's very kind of meta, very mind-warping, and I think very fun. So take compiler construction if you're interested in optimization, and we'll go into how that works. And if you like discrete, you'll enjoy it because it uses a lot of set theory and math to characterize the the optimizations. Okay, other questions on addition, subtraction, and multiplication? So all three of those will work the same way. Make sure you get the order of operations right, because subtraction is not commutative. And all three of those have basically the exact same template, or that's the easy way, I think, to generate this code. All right, let's do division. So division in Intel's architecture is a little bit more nuanced than addition. So for one, there's only specific registers you can use. You can't use, so in addition, you can use virtually any register to do addition. For division, you have to use specific registers. And also, when you do division and remainder always happen at the same time. They're not two separate operations. It's one division operation, and it always computes the division and the remainder. So, taking computer organization, why might the architects design the chip like this? What benefit? Why not make it easier on the assembler programmer?
Simplicity, it's for them.
Yeah, I think simplicity for them, right? So you only need to hook up registers to one division submodule, or whatever they call it in the architecture world. And division and remainder, you might as well do it together because you're already computing it. It probably doesn't cost much more to compute them together. That's my guess. I'm not a computer architecture person, but I think this is why they did it this way. In MIPS, division, is it any register, if you remember? Do you have division? You don't even need division in the architecture, right? You could actually simulate it with subtraction and multiplication. Okay, so let's look at how division works. So I'm going to just go over the operations first, make sure we understand these, and then I'll talk about the compilation strategy for doing this. Okay, so just like for subtraction and everything else, we're going to first set up the registers. We're going to just give ourselves registers for these. So for instance, I'm going to store 9 into RAX and 5 into RBX. So now I've set myself up to have the, for whatever, the move operations, if they're variables or integer constants, it doesn't matter. I just make sure I always use the same registers. So RAX must hold the numerator in the division in the Intel world. That's the only register that can hold the numerator. So you must put it in RAX. Now this is where things get a little complicated. The Intel divisions actually supports the x86-64 one supports a 128-bit, not 64-bit numerator to the division. Now we only have 64-bit numbers, so there's a special operation that will convert this 64-bit number effectively into a 128-bit number. The way they do it is they pair two registers, the RDX register and the RAX register. So these are details of the Intel architecture that you probably never need to remember just for this class. But you're basically taking a 128-bit number and the registers are only 64 bits, so you take two 64-bit numbers, put them together, and you get a 128-bit number. That's your numerator. But since we don't have 128-bit numbers, we use this instruction here, CDQ, to sign extend RAX into RDX. So if you remember, like 2's complement, how negative numbers are represented, the left, the most significant bit's always going to be 1. So this will just make sure that if RAX is negative, RDX is going to be like all 1s, or all 0s if it's positive. So anyway, so if you don't worry too much about the architecture, just follow this template, and it should work correctly. And then here's how we issue the division. So IDIV is integer division, and it's going to divide this combined 128-bit number by whatever register we pass into div. So the numerator will always be in RAX, or really RDX and RAX, but you can give any divisor you'd like. So because we put the divisor, divisor in RBX, then this IDIV instruction, even though it only has a single operand, it's actually dividing RAX effectively by RBX. Questions on that? So this is Intel's kind of very special purpose style design to its architecture, to its language. And now you don't know, it doesn't even tell you what the destination is. Those are in fixed registers. So the destination of the quotient, that's the result of the division, will always be in RAX, and the remainder will be in RDX. So whenever we do the division, your division result will be in RAX, and the remainder will be in RDX. no matter what the other operands are, no matter what you give to IDiv. So you just kind of have to know or remember this. So you can see what really compilers are doing. They're translating from one language to another language that may have very, very different behavior, very, very different semantics. Okay, questions on this? Questions on division in the x86-64 world? And so I give you I have examples of all this, so you can, again, be very template-driven about this. So for addition, subtraction, multiplication, you can use that template that I gave you a couple slides ago. And for division and modulo, use this template. So use IDiv for both division and modulo. Do the same thing as we did for other operations where we set up the registers. And then what's different here is we have fixed registers to retrieve the results from, but we still just store those results into a variable in the same way. All right, so let me show you a full example of this. So here's our division statement, our division operation in simple IR. And here's our assembly code. So what's the first thing we do? We load the operands from memory. So we load A and B. So we load the numerator into RAX, and we load our divisor, I think it's called, into RBX. So questions about this part of the code? Hopefully it's review. Okay, so now remember, RAX must be the register you store the numerator in. So now we issue the division. So for our purposes, the division will always do CDQ. That's that sign extend thing. If you don't remember, don't worry about it. Just always do CDQ. And then issue the IDiv giving only the denominator or the divisor as the argument. So that was what we set up as the bottom of the division, the right-hand side of the division, the divisor, the denominator. Questions on this? So it looks very much like multiplication and division, right? Or multiplication and subtraction, right? So we have the same operand setup. Instead of having a single add with two operands, we have CDQ and IDiv with one operand. And because RAX, in this same way, RAX holds the result of the division, we just take RAX and store it into the memory location associated with X. Questions on this? So if you see, the pattern is very close to addition, subtraction, multiplication if you use this strategy that I'm recommending. Yeah?
So CDQ always knows to do that sign extend for RX and RDX. You don't have to pass any first.
No, yeah. Again, so it's only for RAX. It's only for RAX. Only the numerator is 128-bit. And because division is like hard-coded to only use RAX, CDQ is similarly hard-coded to only use RAX. And it also overwrites RDX as well. So division and CDQ, RAX and RDX are special registers that division only uses. Division modulo and CDQ only use those two registers for its numerator. So yeah, it's a little, you just have to know the behavior of the Intel architecture. It's not like MIPS where it's a little cleaner, kind of simpler design, the RISC design. But you can see these three steps are really similar. So this first step is the same as for other operations, and the last step is the same for division. This is the only thing you swap out. So hopefully you can start to see maybe a compilation strategy here, where for operation, no matter what the operation is, you always do this first. You always do something like this last. And then you just swap out the operand you use, the mnemonic you use in the middle. Okay, so let's finally look at modulo. So how will this, if you remember the behavior of the Intel architecture, how will this assembly code change if we want the modulo instead of the division? Yeah?
Remove RBX instead of RAX.
Cl-
Stores the
R-
register, right?
would-
We're putting mod RBX, right?
So close, it's RDX.
Oh.
So I don't expect you to actually remember this. That was really good, but you remembered that there are special registers that division stores into. It's RDX that stores the divisor. So RAX and RDX are the special registers that division uses. And so notice that it uses them both as the numerator and as the result. So the numerator is RDX, RAX, and the results are in RAX and RDX.
So I did and CDQ are like functions like in and of themselves, and like they know to go to RAX.
Yes, they're Intel operations that are like effectively hard-coded with RAX and RDX. But yeah, you're exactly right. You got it exactly right. So the thing that would change is this. That's it. But it would be RDX is where the modulo, the remainder, will be stored. So the only difference, this is the original, store RAX, which is the quotient or the result of the division. For modulo, you use RDX. So very sort of minor architectural stuff. Just use my code generation guide. Use these slides to remember them. Questions? Any other questions on this?
How would you process an exponent?
Oh, so the question was exponents.
Yeah.
So the Intel architecture doesn't have any single instruction for exponents. So how might you, actually we kind of did this a couple weeks ago when we talked about, so let's say SimpleIR had an exponent operation. How could we generate code in assembly that would give us the exponent?
I would think like some sort of for loop, I guess.
It would be like a for loop, and you don't have for loops in assembly, so you'd have to generate code with branching and actually write code in assembly that computes an exponent operation, and then whenever you see that in your input, actually spit out that entire block of code. That's how you would do it, yeah. So as long as the languages are equivalent, that is, you can compute the same stuff in both languages, you can always translate between them. So this is the Church-Turing hypothesis, that there is this it's a hypothesis, or Church-Turing thesis, that there is a notion of computable numbers, and both the lambda calculus and recursive functions and the Turing machines, they're all equivalent, and they all represent computability. This is the thesis. It's not really provable. It's sort of an assumption in computer science that there is this kind of core language that defines what all computation can be, and as long as your language can be translated into those, you can translate freely between any programming language. They all are equivalently powerful in what they can compute. So that's more of a theory of computation thing, or discrete too. I think we'll talk about it. So take that to learn more about that. It's kind of cool foundational results of computer science, and it's kind of what makes compilation possible, that we can always translate between these languages, even if you don't have a specific operation for it. Same thing with floating point too, by the way. So early processors didn't have floating point operations. They'd be simulated in software. You'd write functions to do floating point arithmetic. And then architects started putting a floating point coprocessor. They added a separate chip, and now they're in most commodity chips just have ARC. So that's why we use idiv here, because there's a different division for floating point. It's actually a different operation. It's not the same division operation in the assembly world. All right, other questions on operations? Yeah.
What was it? It was CDP.
Yeah.
So does idiv undo that connection?
Well, idiv will overwrite RBX and RAX. So whatever values you had in RAX and RDX here, division is going to blow them away, because it just overwrites RAX and RDX. So yeah, it effectively undoes it. So this is also why, especially in the Intel world, because you only have two operands, and you have a destination operand. That's why we need to be really careful about how we represent variables. So in this compiler, the scheme is always pull it from memory, or always load it from memory, and always store it to memory after every operation, no matter what. Don't try, you could play tricks with keeping them in registers. That'll be more efficient. But keep in mind that we can always use optimizations. We can always do later translations to improve the code. So even if you see silly things like move 9 into RAX and then move RAX into memory and then move that same location back into RAX, very wasteful code. But we as the compiler writers, to make it easier on ourselves, don't worry about that. We just emit code that's equivalent, correct before perform it. Premature optimization is the root of all evil, if you've ever heard that. So correct first, then perform it later. And generally in software engineering, follow that, because you may be spending weeks optimizing something that's like 1% of your whole system. First, profile your system. If you reduce 50% of your system by 5%, that's better than reducing 1% of your system by 90%. If that makes sense. What was that?
Worry about getting it done first.
Yeah, worry about getting it correct first. Yeah, and then you'll have a better idea of where you need to do performance optimization. Same idea here. So correct compilation first, and then there are all sorts of techniques for making the code more efficient after that. All right, so that's 10:20. All right, everyone. So homework's up, and see you next week. Yeah, sure.